Okay, now we are going to draw or sketch the shear and moment diagrams without using the shear and moment equations. Okay, so we are just going to use the relationship between the load, the shear, and the moment diagrams. Okay, so before you solve a problem, we have these things that we need to remember and understand. Okay, so for example, if we have a simply supported beam and it is loaded like this. If we are going to consider a very small part of the beam, let's say this part, at a distance of x from the left end. So this part is very small, we can call it dx. Okay, so if we are going to draw that here, small part here. So we have the, let's say, load here, and then on the left side we will have the shear, and on the right side we'll have the shear in the opposite direction. Now because of this very small distance, d sub x, there is already a change in shear, so that on this side the shear will be V plus dB. So this is the load W. We are going to sum up forces vertical. We will have this one going up plus this is also going up. That would be the intensity times the distance, which is dx. This one is going down, that's minus V plus dV equals 0 for equilibrium. So this becomes minus V minus dV equals 0. So V minus V is 0, this is 0, and we'll move this to the right, or we add dV to both sides of the equation. We will have W dx equals dV. We need to remember this one. Okay? So let's write it here. W dx is equal to dV. We are going to integrate this. So this is point, let's say x1. Here is x2. So we're integrating with respect to x. So the limit would be x1 up to x2. This one will be shear here. Let's just call it shear 1. And the shear here, let's call it shear 2. So if we are going to integrate this, it's just the area under this curve from x1 to x2. So we'll just write area of W, which is the load diagram. So let's just write area of the load diagram equals V, and the limit is from V1 to V2. So the area of the load diagram is V2 minus V1, or this is just the change in shear. So let's write it here. V2 minus V1 is equal to the area of the load diagram. Then here there's also a moment. Let's call that M. And here the moment will be moment plus Pm. So if we sum up moment here, that will be this one, M, plus the moment created by V, which is plus V times dx. So that's V times the distance dx, plus the moment created by the load W, that will be W times dx, times the moment arm dx over 2. And then this one is minus M plus dm equals 0. Okay, if we look at this third term, this one here, this dx is very small. And then if we are going to multiply another dx, that will be dx squared. That would be very small compared to these terms here. So we can just neglect this one. So we will have m plus b dx minus m minus derivative of m equals 0. So this m will be 0, m minus m is 0. We have b dx equals dm. So again, let's write this one here. v dx equals dm. So to solve this, we need to integrate. So we're integrating with respect to x. So our limit will be from x1 to x2. This one will be m1 to m2. So integrating this with respect to x from x1 to x2 is just the area of the shear diagram from x1 to x2 equals the integral of the derivative of m is equal to m from m1 to m2, or this is m2 minus m1, or that is the change in moment. So we'll write it here. m2 minus m1 is the area of the shear diagram. So we have to remember that the change in shear in the shear diagram is just the area under the score of the load diagram. Then the change in moment is the area of the shear. Then from here, w dx is dv. That means our w is dv over dx. Now this dv over dx is actually the slope of the shear diagram. Means the intensity of the load is equal to the slope of the shear diagram. And this v dx equals dm will give us shear is equal to dm over dx. dm over dx is the slope of the moment diagram. And last is a positive slope is going up or increasing from left to right. It's going up. And a negative slope is the opposite. It's going down from left to right, or it is decreasing. So the things we need to remember: the change in shear, the shear diagram is the area of the load. The change in moment in the moment diagram is the area of the shear. The slope, the shear diagram is the intensity of the load. The slope of the bending moment diagram is the magnitude of the shear. Positive slope is going up from left to right, and negative slope should be going down from left to right. Okay, so let us now solve again the same problem we have solved using the shear and moment equation. But this time, we will not use the equations. We'll use the relationship between the load, shear, and moment. £270 per foot. Reaction R1, we already have solved this one. That is equal to 450 pounds. And this reaction here is 360 pounds. This is one is 6 feet. This one here is 3 feet. So let's draw the shear diagram. So we will start with the reaction 450. It's going up, so it should be up here 450. So the only time there's an abrupt change in shear is that when there is a concentrated load on the load diagram. So that's 450 going up, and then forces going down will be negative. The change in shear, if we call this V sub 1, the shear here, we'll call it V sub 2. So V sub 2 minus V sub 1 is the area of the load diagram. So V sub 2, we do not know. V sub 1 is 450. The area is, as a triangle, 1/2 of 270 times 6. So it's going down, so this will be negative. So V sub 2 will add 450 on both sides of the equation, will be 1/2 of 270 times 6 equals negative 360 pounds. So 360 is 60. So it's about here, negative 360 pounds. So how are we going to connect these 2 points? So again, it's the relationship between the load and the shear. So the intensity of the load here is 0. And we know that the slope of the shear diagram is the intensity here, meaning the slope here is 0. So if we're going to draw a line, slope is 0, it's horizontal. It's not going up, it's not going down, it's horizontal. So that's the slope at this point of the shear diagram. Here, there is a intensity of 270. It's going down. So that is a negative slope. So negative slope is going down from left to right. So we can say this is the slope. It's going down like this. So if we are going to connect these 2 points, considering their slope, the diagram would look like this. It would be tangent to this line, and then tangent to this line here. So this is second degree. Then over here, there is no load, so there's no change in shear. That means our diagram will have a horizontal line here, negative 360. It goes up because of this one. Next, the moment diagram. Okay, over here, there's a point where the shear crosses the zero line. So meaning the shear here is 0. That means we need a distance from the left to this point so we can solve the moment this point, which is the maximum moment. Okay, so first we will solve for this distance. Let's call that x. So how are we going to solve that one? So there is this property of a second degree curve or a parabola. It's called the SPP, or the squared property of parabolas. It states that y to the square of x is the same or equal to y sub 1 or x sub 2 square. So using this, okay, so we have a parabola. It looks like this. This is the point where the slope is 0. And let's say this point here is this point here. That is 6 feet from here. And this is total of 360 plus 450 because we start from here going down here. So this will be 450 plus 360 is 810 pounds. And then somewhere here, this one, this we do not know. Let's call that x. But this is this distance, which is 450 pounds. Following this one, and we'll have 450 is to x square equals 810 is to 6 square. So that our x square is 450 times 6 square is 36 divided by 810. Then x will have two values plus or minus equal to plus or minus 4.8 47 feet. So obviously we will use the positive value. So this one therefore is 4.47 feet. That makes this 6 minus 4.47 is 1.53. Now we will proceed solving the areas. So for a spandrel, if we have a spandrel, it's to the n, where n is the degree of the curve. And this is our base, this is our height. The area of the spandrel is n plus 1 times the base times the height. So in our case, this is 2 or second degree. So the area is 1 over 2 plus 1 is 3. 3/8 is 1. That's the area. If you look here, the area we are going to solve is this one here. Okay? So if this area is 1/3 of BH, meaning this one is 2/3 of BH. Okay, now let's draw the moment diagram. So for moment diagram, we will start at the left end, which is, this is simply supported beam. That means there will be no bending moment here at the end. Then we'll go up to here. So let us solve the moment here. Let's call that moment M2. M2 minus M1 is the area of that portion of the shear diagram. So we know that M1 is 0. So our M2 is the area of this one. Again, that will be 2/3. The 1/3 part is this one here. So this is 2/3 of the base, which is 4.47, times the height, which is 450. So this is 1,341 foot-pounds. So it is somewhere here. 1,341. Okay. So how are we going to connect these 2 points? So first, the obvious is this part here. The shear is 0, meaning the slope of the moment diagram here is also 0. So that means for a 0 slope, we will have a horizontal tangent line. And then here, there's an intensity of 450, positive 450. So positive slope is going up from left to right. So the tangent line might be like this. Okay. If we are going to connect these 2 points, considering this are the tangent line of these points on the curve, then our curve will look like this. Tangent. Boy. Okay. So this is now second degree. This is third degree. Okay, next we are going to solve for this area. So for this area, we cannot use 1/3 BH here. Why? Because this line is not tangent at this point here. So for a spandrel, one of the base should be tangent to the curve. So this should be tangent here. However, there's an easier way to find the moment here. We will use this area here. So that would be, if this is M2, M3, M4, M4 is 0. M3 we do not know, but we can solve this area. So that means M4 minus M3 equals this area here, which is just the area of a rectangle. That's negative 360 times 3. Again, this is 0 minus M3 is negative 1080. We divide by negative 1, M3 is positive 1080 foot-pounds. So that should be here. We have 1080 and 0 here. How are we going to connect these 2 points? If we look at the shear diagram, the magnitude of the shear is the same all throughout from here to here, meaning the slope here and the slope here are the same. So that slope should be like this. So the slope here is like this, and the slope here is also like that. It's very obvious we will connect that with a straight line. How are we going to connect this? We already have the slope here and we have the slope here. So just draw a curve tangent to both lines and it should look like this. So this is our moment diagram. But it just so happened that this area here is easy to solve. And we know that this moment here is 0. So we can get it. But let's try and solve this area. And let's try and solve this area. Then we'll subtract that from 1341. Let's see if we can solve that one. Okay, let's draw the curve again here. Okay, so this line here is tangent to this point here. That means we can use the formula area is 1/3 h. This height here, h, this will be our h for this spandrel. So we need to solve this spandrel. We have to start here because this is where this line is tangent to the curve. And this distance is 6 feet. This one is 450 plus 360 is 810. Okay. Let's call this area 2. Area 2 is S1, 1/3 of 810 times 6. But we are solving for this area here. We only need this part here. But we know this distance also, this one here. Here. This is 4.47. And we also know this distance, that's 450. So if we are going to subtract that area, we will subtract this area here. And that area is 1/3 of 450 times 4.47. Now we have this area. Then we know this to be 1.53. So if we will subtract this part, that's minus area of the rectangle 1.53 times 450. So what's left is this part here, area 2. Area 2 is equal to 261. So if this is 1, 2, 3, M3, and this is M2, the change in moment from M2 to M3 is equal to area 2. But this is a negative area here, it's below the 0 line, so just write minus 261. So M3 equals minus 261. This becomes plus M2, and M2 is 1,341. So M2 is equal to 1,080 foot-pounds.